So it's my great pleasure to introduce John Hershey, my team leader at MERL. And so John got his PhD from UCSD, and then went to be a visiting researcher in the speech group at MSR, then joined IBM Research Center, and led the speech enhancement team there, and then joined MERL in 2010. He's going to talk today about his latest and greatest deep clustering discriminative embeddings for segmentation and separation. Thank you.
Thanks a lot for the introduction, and really happy to be here. I want to start by just saying that the topic here is separation of challenging sound combinations that we don't usually get a chance to sort of attack. And we haven't, this is very preliminary results, and we haven't taken it to its sort of logical conclusion, but we're very excited about this kind of approach. So just to back up to speech enhancement sort of goes in cycles every time new methods are developed. We kind of start at the simpler tasks and work our way, from stationary noise or quasi-stationary noise to less stationary noise, and more challenging things with speech in the background or something like that. And like at the furthest extreme, you could imagine separating any old arbitrary sounds from one another. We're not there, don't worry. But that's what we would be shooting at. But in the meantime, this is sort of challenging task in speech enhancement that we can make progress on already.
In a fundamental sense, the equity markets have very little to do with what goes on in the commercial banks.
So that's taken from Chime 2, and this is the clean. So the goal here is to pay attention to the boring sound.
In a fundamental sense, the equity markets have very little to do with what goes.
That's almost unachievable because some of the sound is obscured. Some of the sound that you wanted to pay attention to is obscured. But the approach we take is to basically ignore that and analyze noisy speech, look at the spectrum domain, and then we found, after going through many different models over the years, graphical models and NMF-based things, the deep networks just so far work the best. Like everybody else, we're finding that they can sort of sweep away a lot of the very intricate and clever things that we came up with over the years. And the approach that we have taken is to estimate a mask function, which is then applied to the input spectrogram. And the reason for that, well, the way I justify that is that when the signal is clean, you really don't want to hurt it. And the type of deep networks that we've been using are nonlinear. In some sense, we're just adding a gating function so that they can be linear. They can choose to be linear when they want to. And that's what this mask is. It's just the network choosing to be linear or not. So then after application of that, there's an inverse Fourier transform, and we get out a clean speech estimate. So to further justify this sort of masking approach, which the reason I'm talking about this is because the deep clustering approach that I'm going to talk about later is right now only done in the sense of inferring a binary mask. So I'm trying to, even though I'm not a big fan of binary masks, and I think we can always do better, they're actually important, and I just want to say why they're important. So here we have just a single frame spectrum containing a mixture of male and female speech. So the female is in red and the male is in blue. And the black line is the spectrum of the sum of the two. So they're added linearly, but it's just the spectrum of the sum. So you can see that when one of them clearly dominates the other, when one is louder than the other, the sum is the same, as obviously, as that one, and vice versa. There are some regions where it's not the same. That's when the SNR is very sort of close to 0. But there's no way, in the cases where one of the signals is dominated, like here, the blue is the male speaker is dominated by the female, there's no way to get back that information other than by looking at the part that's not dominated. Right? The only information we have about that region comes from the other part that is not dominated. And it's just a zooming out to like so 3 sources. It's very hard to see what source is dominating where. But if you knew that, now those things start to look like speech spectrograms. And my claim is that aside from those little areas where it's close to 0 dB, really all information about all of the sources can be observed directly once you know the mask. And I'll have some computational arguments later about this. But for now, I'll just play what it sounds like.
Yeah, I get. In a fundamental sense.
That's that one again. And this is.
In a fundamental sense, the equity markets have very little to do with what.
So you've all heard that stuff before, and there's tiny artifacts in there. I don't want to dwell on it just to try to avoid running out of time. But what we do then is, with our network, like many other people, we use a long short-term memory network, and in this case, we found that it works the best to use a bidirectional one, and I think they've already been talked about, so I don't need to explain them in too much detail. Just a lot of gating and some linearity down the middle. The results we get sound like this. I'll just remind you of the beginning of the noisy one.
In a fundamental sense, the equity markets have very little to do.
Yeah, it's fun.
In a fundamental sense, the equity markets have very little to do with what goes on in the commercial.
So we have a fun to boring converter that gets rid of kids. But you could run it the other way. We can estimate the fun part. I don't know why we just showed this part. But there are some serious issues now if we want to keep following our progression towards more difficult and challenging things, because there's some things that don't come naturally for deep networks the way they're currently configured, and the rest of the talk will be explaining that and how we get around that, or what our solution to those problems is. So the problem that I'm referring to is when you're trying to separate different sources that are of the same class. So you could think of that previous network that I showed you as basically classifying. It takes in the whole spectrogram and is basically classifying each time frequency bin. Should this one be considered this source or that source? So it has an output for this, slot number 1, we'll call it, and an output for the other source, slot number 2. And of course, if you have 10 sources, you've got 10 outputs. So it has to make a sort of a decision about which thing to put where. So now, say we have a speaker-dependent separation case. So we have a network trained to separate this speaker and that speaker, which some people, amazingly enough, have done. So I guess you would have to do all possible pairs of speakers in that case. Have a network for each possible pair. Anyway, so it's outputting some classification result. It says this time frequency bin belongs to speaker 1, and this one belongs to speaker 2. Fine, that can work actually. But if they're speaker independent, then what? The problem is that how would it know which place to put a given speaker, since during training it's arbitrary and random which one was sort of targeted to slot 1 and which one was targeted to slot 2. So we call this the permutation problem. There's a permutation problem when there's something symmetric to be inferred, like you have male-male speech. You don't really know which one goes where. And there's some simple ideas to fix that we tried. One idea was already sort of used for speech recognition by an MSR group, where they chose for each sort of frame to have the state of the louder source in that frame be estimated as slot 1, and the state of the quieter source to be estimated as slot 2. And then you later used a decoding process to resolve all those permutations in the decoder when doing recognition, and that worked really well. So there's some hope to get out of this sort of problem, and part of it seems to be applying another algorithm that makes decisions, because without architecting something into the network to make decisions, it's maybe not the best decision making, like global level decision maker. But we tried this. So in our task, we don't have states particularly, and so we just tried to do it sort of at the global level, like, well, let the network output to speakers. At training time, we'll put the louder speaker in slot 1 and the quieter in slot 2. So we tried that. We also tried, since that didn't work, we didn't really expect it to work, but it didn't work. So we also tried deciding after the fact, like the network's going to output whatever it outputs. We'll just pick the best permutation at training time and then keep going from there, sort of like max pooling style. That also failed. And then there's other problems, like what if there are more than 2 sources? So how would you have a network that has a fixed number of outputs and resolves these permutation problems and also decides on the number of sources? It's possible. I don't think it's impossible. But we tried. The way we solve it is kind of like stripping off the end of the network and handling that in a completely different way. This is just showing what you get when you try to train conventional DNN by doing this pick the best permutation approach. So it knows that you want it to label something as speech and the other thing as speech. And so, we call this paradigm sort of classifier-based separation. Like if you have classes with labels at training time and they're different, you can train classifiers to identify which parts of the spectrum the classes come from. But if they're the same class, that doesn't work anymore. So you get something. I mean, possibly this is meaningful. I'm not sure. It's not going to sound good, I can tell you that. So before we go through the rest of the talk, if you have to like catch an Uber or something, I'll just give you the answer just in English, and then later on we can get into the details. So instead of having a slot for every speaker, we say we would like to have the network sort of infer a representation of that structure, a representation of the clustering structure, which things belong in which cluster, that doesn't have that permutation problem. It doesn't have a slot for anything. So the way we do that is make the sort of slotification process a big, broad, continuous embedding space. So now, instead of having a slot for a speaker, you have maybe a region of space or something. We don't know what it's doing, but we train it just so that if different regions belong to the same source, we'd like their vector space embedding to be close to each other. And if they belong to different sources, we'd like them to be far from each other. And it turns out that we can relate this to sort of spectral clustering approaches as well as just simple things like k-means. And it kind of bridges the gap between spectral clustering and k-means and does it in a nice, efficient way. And so that's why we're happy about it. So after training a network to do this, then we can just cluster the points. And then the cluster assignments will tell us the masking function. So this is why we're doing binary masking. But it can be extended to continuous soft clustering and so on. So that's a very good direction to go. But the network doesn't have to decide anything. That's, I think, the nice part of this. It doesn't have to make a global decision about should I put it this A and B or B and A. And we got some kind of surprising, and just like in Ron's case, we have no idea how this could possibly work. It's just kind of amazing. But we intend to analyze it, and we're going to talk to neuroscientists to help us figure out how to do that. But this is a case where we trained it on pairs of speakers, pairs of speech, utterances mixed together artificially. And of course, we tested on that too, but then we fed it mixtures of 3 speakers. And it sort of works. It's a harder problem because, at least in pairs of different of 2 speakers, there's a chance that you have just a male and a female, which is the easy case. And here, you've always got 2 of the same gender, I think, depending on where you do it. And so you get some real separation of things. It's not always correct. So here, the red is one, I can't remember which is male. I think it's one male, and the yellow is another male. And I believe that the light blue cayenne is would be female because the harmonics are more spaced apart. So it's doing really well at the female versus the males. Sometimes it's making confusions within males, but on the whole, like the fact that it handles this beginning part pretty well, and you can see here it's making a mistake, but on the whole, we're just surprised that it worked at all, and and happy to present that. But I think this is one of those things where this was just the first experiment that we tried, and it just seems to do something cool. So, but we should now. I'm going to go back and give a more proper introduction, I guess. And I think for me, I grew up in model-based era, and I always think, well, what about model? And by model, I mean like generative model, probabilistic models, that type of thing. Because there was a time when we thought that was basically the only way to handle this kind of thing. Like you have a model for one source, you have a model for another source, you let them fight it out for control of the input, and you infer the state sequences. And so we went down that road, me and my colleagues at IBM, Steve Rennie, who's maybe here somewhere. And so we made HMMs for speech, and of course back then it was okay to have really small kind of problem spaces like a grammar with 50 or so words in it. So we made these HMMs and then combined them using an observation model. And so we've had this kind of, thanks to Steve for this slide, model combination approach where, in the limit you would have to say, well, I'm just going to have a model for every type of sound that I ever want to handle with this. But it might be okay. And maybe you could even dream about having some kind of general model that could generate any sound. Like, it's possible, but it's complicated to do that. The inference, the interaction, I'm blowing in the mic over here. The interaction between the domain where you're doing enhancement and the domain where you're representing the model of the signal and the domain where the signals are adding up is almost always different. And so handling that, we use model-based methods where we said, oh, I'm going to assume this form of combination function for the different things. So this is the yellow one down there is what you get if you model things in the log domain and you look at linear interaction. We called it, when we made this plot, we were trying to decide what to call it. We ended up calling it the devil function because it was just a total pain. It goes up to infinity around the edges. And so the common approximations that people use are just max model or sum of the powers, which are both strikingly wrong if you look at that picture. Anyway, so we went down that road, and nevertheless, we were able to do amazing things. We were able to separate like 4 speakers, of course, not without horrendous approximations to the model. I mean, you just can't. The number of states in a combination of 4 HMMs is astronomical, so we have to use astronomy. And we used variational astronomy. But look, I mean, this is the middle one is the clean, and the bottom one is the estimated. This is 4 speakers mixed together. This is the mask that you get. I mean, it really worked well. It's just too bad we could only process like 100 files because, it's very slow. But just to hear what could be possible someday with neural networks.
Place right at D00 now.
Can anybody give me the transcription of all 4 of those? Would you like to listen to it a few hundred times? You can't. That's humanly impossible, and yet
Place white at D0 soon.
Place red on H3 now.
Play blue at P0 now.
Place green with B8 soon.
I think we had a loose connection as well, so tighter connections could do better. So it's a very constrained task. It's not realistic at all. It's known set of speakers, closed set, you know, many, many, many things that help this to be possible in addition to the variational inference. But hey, you know, it's pretty impressive, and it's a modular system. You can throw more models into it and do it with 10 speakers if you want, I guess. It's not going to work that well, but anyway, the problem is, you know, that huge sort of exponential intractability that comes when you have, I'm going to try to point with my mouse again without going to the next page. When you have all these different state variables and you have to look at all combinations of them, and of course, you know, we did all sorts of things to try to make that faster. And what we ended up with for that particular, this was Steve's idea, for that particular 4-speaker thing was to alternate between looking at the posterior for the state sequences and looking at the posterior for the masks. Because if you know the source states, inferring the masks is trivial. It's a linear time operation. It's fast. It's just like doing speech recognition. You just run Viterbi. And if you, did I say if you know the masks? That's what I should have said. If you know the masks, getting the states is just running Viterbi. If you know the states, getting the masks is also trivial. It's just because you can analyze each time frequency bin separately. You know the state of the model at that point in time, so you know its distribution, and figuring out the probability of one source dominating the other is trivial then. So, I mean, you go from something that's NP hard, exponential problem, inferring both the states and these masking probabilities, to something that is linear one at a time. So that's why we did that variational inference algorithm. And this is maybe a side issue, and I'm not keeping track of time. So, but I'll just say it. So NMF is a little different, and there are other continuous models that, you know, they're basically, NMS is a bilinear model. And it has the same property, though, that if you know one of the components, you can infer the other. If you know the other, you can infer. But you can't optimize them both together very well. And so I think it's a thorny fundamental issue. I don't think it's just because we're doing discrete state things that blow up exponentially. So, and we want to sort of avoid this iteration and iteration, right? I mean, this is one of the reasons why we think deep networks are good, because you can optimize them on a budget to get their job done after a certain number of layers rather than exponentially decaying towards an answer 400 iterations later. So, but the main point for this is, since we're using deep clustering to get binary masks, if you can get good masks, you're almost done. Like, then just get the states. It's fast. So that's the computational argument. And then the other thing one could do with model-based things is we have these deep unfolding methods that we're not going to talk about here, but the basic idea is to take those iterative algorithms and turn it into a network and then put it on a budget and train it. And so there's a lot of interesting things one might do there. It's just another direction, so I'm not going to criticize it too much since we came up with it. I'll leave that to you guys. Try to stop breathing. Downward. So deep clustering, what is it? What are we talking about? How do we do this? One more background slide, which is to say that you could kind of relate deep clustering to Gestalt type of things, because after all, it's grouping, right? So, and the audio Gestalt thing is called CASA, computational auditory scene analysis. And the idea was we're just going to look at all the Gestalt laws and come up with rules for combining them together. You know, look at the proximity in time and frequency, look at amplitude modulation, onsets, offsets, frequency variation in common across different things, and cluster things according to how they match those similarity aspects, harmonicity being one of the major ones. But you know, there's no learning necessarily involved. In history, when people tried these things, there was no learning. Until later on, Bach and Jordan had a paper in 2006 where they were showing how you can do learning with spectral clustering. And so they did multiple kernel learning. Multiple kernel learning means you have a bunch of similarity functions, but you don't know how to combine them. So you put weights on the different similarity functions and you learn those to solve a clustering problem where you have labels. So that's good, and we sort of take inspiration from that. And the other thing, though, is that one of the problems with that approach is that when you analyze the input to try to say, oh, is this time frequency bin similar to this one? Well, you can't just look at one time frequency bin because it's just a number. So you have to look at a patch or something. But that patch, I mean, this is a patch from their paper. That patch might be sorry, this is not, they didn't actually use a patch of that size or anything. It's just my cartoon based on the spectrogram from their paper. But you know, whatever patch you choose, it's going to be looking at some of one source and some of another source. So how can you measure the similarity of that patch to another patch, which is also a mixture of the two different sources? Are you measuring the similarity of the things of the sources or just the patches which contain both sources? So you have to do much more advanced things than patches, and that's what they did. They used a graphical model with a factorial dynamical system to track the pitches, and then they fed those features into their spectral clustering thing. So in some sense, you know, that's just sort of going back to the model-based approach. But now we have deep networks, so our hope was that we could just let the network solve the hard problem of that catch-22. Like, you need the mask in order to get the features, in order to determine the mask. It's kind of similar to the state versus masking function thing. I don't know how similar that is, but kind of similar. So just diving in, hopefully won't have to talk too much about all the math. Anyway, suppose so at training time, you could say, we're going to take two files, mix them together, and get a binary mask. So we have a label for that thing. Is this time frequency bin in source 1 or source 2? And the source, which source it is arbitrary. But we can make that label sort of thing, which, so I here represents time frequency bins in our case. And C is which source, which cluster it's in, you could say. Without too much fuss, YY transpose is just this big matrix where it's just measuring whether those things are in the same cluster or not, because you're taking the dot product of a vector that indicates which class it is with another vector for another time frequency bin which indicates which class it is. So that's 0 if they're not in the same class, or it's 1 if they're in the same class. So if yi equals yj, two different time frequency bins, then it's 1. Otherwise, if they're unequal, since it's a one-hot vector, then it's 0. If you know A, you can just cluster. I mean, it's trivial to get the clusters. So one could then, say, take a network and feed it X, like the whole spectrogram, and have it estimate A, the approximate affinity matrix. But they're big. So you don't want to do that. I mean, even spectral clustering methods can't really scale up without making an approximation, because the affinity matrix is just too huge. It's n squared in the number of points, number of frequencies, number of times, very, very big. So they make low rank approximations to their approximate affinities. Our approach is the opposite sort of tack. We say, oh, if we're going to have a low rank approximation, let's build that into the estimator, so that we're going to define the affinity matrix to be a low rank construction. Sort of by construction, it's low rank. Just like the ideal one, by the way, which is YYT. That's extremely low rank because it's just the number of sources is the rank. And here, VVT is the number of embedding dimensions is the rank. And there's good reasons to think that shouldn't be very small, because there's many different types of sources and states that would have to get added together. And you need the network to be flexible because it can't make decisions. So then working a little bit forward then, so then we define this V, so VI is the embedding for a particular time frequency bin, and I don't know why there's not an I on the H, but imagine that there is one. And we constrain them to be unit vectors, just because it's convenient. That means that when they match, their product is 1, and when they're orthogonal, it's 0. So then when we take our approximate, the network-produced affinity matrix VVT, we can compare it to the ideal one, YYT. And the beauty of that operation is just that now there's no permutation in there. There's nothing in YYT that says how its columns are permuted. We could put a permutation matrix after Y, and its inverse, its transpose, before YT, and the product of those is identity matrix. So it's completely rotation invariant and permutation invariant. And so when we write this simple objective function, if you write it out, it leads to the second line, and I'm just going to skip to the next page because it's still written there. And the neat thing about this is that then what it's saying, if you unpack that, is that when they're in the same class, you would like to have their distance go to 0. So you're minimizing. This is a cost function. You're minimizing. So vi minus vj squared, you want that to go down. You can ignore the -1. It's there for technical reasons to make this identically the same objective function as k-means if you were to have weights in there, which I didn't put in for clarity. But there's some weights that k-means would use to make the clusters equal sized, approximately. So then the second term is saying, well, all points, regardless of whether they're in the same class or not, should be not at the same point. They should be pushed apart. It says that I want the distance between the points squared to be around 2. That's the distance squared for orthogonal points, because if they're unit vectors and they're orthogonal, then it's so it's pushing them to be orthogonal, basically. But except if they're in the same class, then it's pushing them to be the same. So that's the objective function. It is the same objective function, coincidentally, as k-means. And what this means is that at training time, you're saying, I'm going to tell you the cluster assignments, and I just want you to manipulate the data points so that they minimize the k-means error, which is the sum of the squared distances to the centroids to the centers of the clusters. That can easily be expressed as the pairwise sums of the distances, which is why this is the same. And at test time, then, we say, OK, well, now I don't know the cluster assignments. I just have these points that the network is creating. And so I can run k-means to optimize the same objective function in terms of the cluster assignments. So we thought this was a very nice symmetric situation where you're training it under the k-means objective function, and you're testing it under the k-means objective function. You're just estimating different things during training and testing. Also, the annoying thing about this objective function, I should say, before moving on, is that it apparently has an n-squared property to it, because v is n, the number of points that you're clustering by embedding size. So VVT is n by n. And so this whole thing would be very expensive if n happened to be very large. And it is. So in a 10-second audio clip, you have like 17 billion entries in that affinity matrix, potentially. Of course, you can operate on smaller chunks, and that's a valid approach. But one thing to note is that you don't actually have to compute that big, giant thing, because the Frobenius norm has this nice property that it pulls apart into its terms, and there's a trace expression of it, which means you can rearrange the things, and you get something that's embedding by embedding, embedding squared. So if k is the embedding size, it's k squared instead of n squared, or k by the number of classes, which is even smaller than k. And the derivative also is cheap. It's because once you compute the derivative, you can just regroup the terms and get the k by k terms. So that's nice. So that's it. That's probably you may want to ask some questions about it, but maybe I'll just barrel ahead and try to get finished. because probably I wasn't very clear, so I apologize for that. It's hard to explain. We tested this on 100 frame chunks. That is, we trained our BLSTM neural network. We basically took the old network that we used for enhancement. We stripped off the output layer. We stripped on the deep clustering layer, and then we trained it using the labeled binary mask that we got from the mixing of the training signals. We had 30 hours of mixtures from Wall Street Journal, randomly sampled. We separated. We had two test cases. One was closed speaker set. And the reason for that was we wanted to be able to compare to any other algorithm, and there are no other algorithms that we knew of that could handle the open speaker set case. And then we had the open speaker set case, just to see that hopefully it would generalize. So this is the sort of basic class-based model comparison, where here we chose, since we didn't have a good method for doing this, with other methods. Well, actually, sorry, I should back up. We chose this method because this is the one neural network sort of case. So the BLSM stack there, forgive the terminology, but that just means we're doing this mask prediction for those 3 speakers. A predefined set of 3 speakers that are the 3 speakers in the training set and the same 3 speakers in the test set. And our best enhancement algorithm that gave great results on other enhancement tasks. And the number you're seeing here is the improvement in SNR. So we get 6.8 dB of improvement in dB. The DC global, that's just running the BLSTM with deep clustering to output those embeddings for all the time frequency bins, and then we just take the whole utterance and do k-means on it all at once. And then, of course, we have to allow a permutation because it was a permutation-free method, so the clustering step is what made some decision about what slot 1 and slot 2 were filled with. And then we have to, when we match that up with a test set, we assume that we have some way of choosing the right test case to measure SNR with respect to, just like you would do if you're doing microarray things. So we actually do better with, it's probably not significant, but anyway, we do about the same with deep clustering, where it knows which 3 speakers are there, as with deep clustering, where it doesn't need to know. It's not making any speaker-specific decision about where to put things. And then we had the Oracle case, so that's you'll see that through all the other results. What that is doing it on the 100 frame chunks. And then for each of those, we do the same thing as we did for the utterance. We just choose the best association with the 100 frame chunk of test case. And the last one is Oracle NMF. So this is where we had a large context NMF model with like 10 frames of context, trained individually for each of the closed speaker cases. So you see that come up in the larger speaker set cases as well. So it's trained specifically for those speakers, and then we combine it together at test time. So it doesn't do as well in this case, but it does well in other cases. We'll see some results like that. So now, what about open speakers? So then NMF, you can't do anything there because you just don't have the model that corresponds to those speakers. We also included another Akasa-based method that is completely untrained. It's just completely handcrafted and tuned, and so those are the results for that. And then the cool thing to note is the deep clustering one doesn't suffer any degradation going from speakers that were in the training set to speakers that were not in the training set. And this is the one that I showed you before. So the BLSTM one at the bottom, those are the ones that I showed you before where it just fails. And we tried to give it a leg up because the deep clustering has this gigantic output layer, right? It's, I'll show you that in a second, but we chose 40 dimensions because it worked the best. So it's 40 dimensions times the number of times frequency bins in the output, so it has a lot of parameters. So we thought, well, we should give the BLSTM a chance by ramping up its parameter size to the same and see if it's just the number of parameters that would be the difference. But that's not it. We also, these were also trained by randomizing, and in another case, which gave about the same results, we initialized it with the model that we got from the deep clustering training, and it still didn't work. So I don't know. You never know with neural networks. It could just be us. But so if someone else has tried it, you can let me know. What about the embedding size? So 5, 10, 20, 40. After 20, it's pretty stable, so we don't really know. It looks like 40 is the best here. And logistic versus tanh. So we had this funny structure where, since we were just using sort of standard LSTMs, they have tanh or logistic outputs. And then we, after projecting to the embeddings, we have to normalize because we wanted to have unit vectors. So we have an additional normalization at the end. You could maybe think about having linear or something like that. Anyway, it didn't make much difference if you compare the 40, the k equals 40, to the k equals 40 logistic. So it's tanh k equals 40 versus logistic h 40. The numbers are about the same. So let's just listen to some results, and then I'll finish up.
A loss wasn't
Michael
unexpected,
Schwartz,
given
a
continental
partner at
operational
Watchtower
difficulties
Linton,
that developed in the
said,
Okay, and so this would be Oracle NMF.
A loss wasn't
Michael
unexpected,
Schwartz,
given continental
partner at
operational
Watchtower
difficulties that developed in the quarter.
Michael Schwartz, a partner.
Okay, so not bad. This is knowing the speaker, having the model train on those speakers in advance.
A loss wasn't unexpected, given continental operational difficulties that developed in the
Also, not bad. Maybe a little bit better. There's artifacts, though. I mean, I would.
Michael Schwartz, a partner at Watchtower Linton, said,
I wouldn't want to say that this is doing the best I've ever heard. I think our old speech separation results were better than this, but that was a very honed model that a lot of people worked on for a long time, and we just threw this into LSTM, and with this particular objective function, we're just getting this right out. Here's same gender.
Mr. Steinman, the Beer newsletter publisher, adds that American baby boomers got hooked on Corona because they can put lime juice in it. Mr. Steinman, the Beer newsletter publisher, adds that American baby boomers.
Not even worth listening to the other one.
Mr. Steinman, the Beer newsletter publisher, adds that American baby boomers got hooked on Corona because they can put lime juice in.
There's subliminal messages in this, by the way. My sponsors won't allow me to say who they are.
European deregulation has been a frequent source of trade conflicts with the U.S. commerce, which blends Europe's current.
So, I mean, this is, for same speaker, this is pretty good. And, there's no language model in here. It's a completely open Wall Street Journal vocabulary. I mean, they're dumb sentences, but, I mean, it shouldn't be prejudiced against dumb sentences. So we're very happy with this. No language model. I mean, how can it even do this? We don't even understand how it works. But generalizes to 3 speakers. Anyway, I think this might have. This was trained. Yeah, 3 speakers trained on 2, right? So this is really tough, actually. And here's in the closed speaker set, NMF has an advantage here over the deep clustering that was trained on 2 and not adapted in any way. It's a harder task for sure, but the fact that it's doing similar on closed and open speaker set is encouraging, and I think if we just trained it on 3 speakers, it would be doing better. Or there might be there's so much to explore here. I think this is just like the tip of the iceberg, because we haven't even looked at. So one neat thing about this model is you can put any kind of features in the input and do this clustering on your chosen output representation that you think is good for separation. But those 2 things are completely independent. I mean, it's looking at the whole spectrogram to get those embeddings. So it doesn't matter what features you use, time domain, microarray features, anything you want. So no factorial decoding. We're currently looking into microphone array things and training through the clustering. K-means isn't the only operation you can do to force the network to make a decision. You can do SVD, would be more similar to spectral clustering, or you could do NMF. So it's kind of like there's many, many chances to do many different new things. Thank you.
If you want, we have time for a couple of questions. If you want to line up behind the microphones, if you do. Steve.
Thanks, John. Nice talk. I'm just wondering, with your experiments so far, if you developed some intuition for if it's actually necessary to use a stronger kernel, or if just increasing the embedding size can essentially make up for that. Like this, if I understand correctly, it corresponds to like a linear kernel, like a cosine symbol.
Yeah, it's a very, very weak kernel, and it just wouldn't work. They don't use it for spectral clustering because it wouldn't do the neat thing that I had some slides on spectral clustering. What it does is it finds local regions where there's connectivity sort of between things, and it builds a graph out of that and kind of clusters on the basis of, you know, looking at the equilibrium distributed, just yada yada. Anyway, but you know, that aspect we can't do with linear kernels at all. Like, just can't do it. And you can see there is degradation when we do the global k-means. It's not as good as doing it separately for the individual chunks. So certainly it's easy to imagine doing some hybrid approach where you allow you know, the beauty of the spectral clustering thing is the signal's changing over time, and it's more like tracking it than sort of forcing it to be at a point. So I definitely think that there's something in between where you could reduce the computational load from spectral clustering and do tracking kind of thing, but just do this basic clustering as a way to get from an embedding to a structured output.
Right. But I'm slightly optimistic that if you blow up the embedding size, that you can do a lot, because I mean, there's randomized techniques where you just do, you know, take 100,000 random projections, and then you implement a Gaussian kernel, say, very accurately. So I don't know, it'd be really interesting to see how that depends on that dimension there.
I think it also that fits into the other follow-up approach, which is to kind of train the rest of the process. You know, like right now we run it, we get an output, then we just do k-means. You know, there's no other process. So to go from 2 speakers to 3 speakers, we just change, you know, k from 2 to 3. But if you had something more advanced there, comparing, looking at the distribution of similarities over time or something, you know. I'm trying to think of something trite to say, like sky is the limit or something. I don't know.
Okay, thanks, John.
I have a question about your objective function. Usually when I see sort of embedding objective functions, you try to make things that are in the same class close and things that are not in the same class far apart. But I think because your objective function is inspired by k-means, it looked like you're also pushing points that are in the same class far away, because you're right. And so and also there's sort of that
k-means doesn't want that, right? K-means wants them all to be close, and our points are not free to move anywhere because they're on the unit sphere, hypersphere. So that term that pushes everything apart sort of arises from that aspect of it, and it's you know, it pushes everything apart. So it's pushing on things that are in the same class, but it's also pushing on things that are in different class. And then you have this other term that's pushing together things in the same class. So the net push is totally different for things in the same versus different.
And I guess you were using that particular structure because you wanted to be able to use k-means at test time.
Yes, you could say that somehow subconsciously we knew what we were doing when we put it all together.
Thanks a lot.
All right, let's thank John again.